Welcome to April 29th's lecture work and classwork that we went over. There's actually two questions that I want to go over, and this is the first one, where there's going to be two rolling cylinders, and we're supposed to use the knowledge that we have earlier, where using the moment of inertia of a hollow object, or a hollow circular object, or so essentially of a ring, or the moment of inertia of a disk. And so what we're going to use is the conservation of energy, where we know that the potential energy, or since energy initial equals E final, let's just have that out, and then conservation so the conservation of energy, and we know that in the beginning it's held still, and just for you guys to know, the top one is the solid and then the bottom one is the hollow. And we have PE, the potential energy, since it's at a stationary moment, but it has potential energy because it's about to fall off, with equals the kinetic energy as it's almost about to, as it's leaving the hill. And so let's set that up, where we have mgh equals 1/2 mv squared. And you might assume, okay, that's all we've learned, or that's what we've learned, the potential equals the kinetic, and that's it. But since the cylinder is rotating, we also need to consider the rotational kinematic energy. And so we know that to be 1/2 I angular velocity squared. And so we have that, and so now we can actually go about in solving these questions. First, let's do this for the solid cylinder. So this is not hollow, this is solid. And what I worked on earlier with you guys in the last class for April 24th, I think? Yeah, for 24th, we know that the moment of inertia of a disk is going to be 1/2 mr squared. And so let's plug that into our equation, or since it is a disk and it is in hollow, it should be I equals 1/2 mr squared, literally what we did last video. So 1/2 mr squared angular or velocity 1/2 mv squared. And so now that we have this, we can cross out the masses because they're present in each thing, so they cancel out, and we get GH 1/4 r squared, and we know that angular velocity is v squared, or v over r, but since it's the power of 2, we square both of them, and we get plus 1/2 just v squared. So that we have this, we can also cancel the radiuses out and get GH equals 1/4 v squared plus 1/2 v squared, which ends up just becoming, this can be 2 over 4, right? So it's, you just add them up, 3 over 4 v squared, v equals, and you move this here, so it'll be 4 over 3 GH, and it's power of 2 square root, and then 4, or square root equals, or v equals square root of 4 over 3 GH. So this is of solid, so let's just mark it solid here. Now, contrary to the solid, the moment of inertia is going to be different for a hollow cylinder. So the approach is still going to be the exact same. The way we approach this question is going to be like how we did here, but instead of 1/2 mr squared, it's going to just equal mr squared. And so in this step right here, it diverges a little bit. So for the hollow, it diverges to where it's going to equal GH equals 1/2 v squared plus 1/2, and then the r squared gets cancelled out because it's just the exact same thing, but instead of it being 1/4, it's 1/2. And so you get this. And since they're both 2/4, that's just going to equal 1, so it's just going to be v squared, and then v equals gh, the square root of gh. So now, given these two, we now know that if they are dropped from the same height, and we're assuming that gravity is going to be the same for these two, since they're both going to be on Earth, we know that the velocity of the solid is going to be greater because there's a coefficient or a constant of a 4/3 in front, whereas the hollow just is gh by itself. And so this question, we went over the conservation of energy, and now we're including and also taking into consideration the rotational kinematic energy, which was 1/2 times inertia times angular velocity. Also keeping in mind how inertia now affects the movement or the velocity of these objects, because once you consider the rotational kinematics, you also now have to take into consideration the inertia, because the kinematic equation for the rotational kinematics, or the rotational kinetic energy includes moment of inertia. And that's really the point of this question, where it's how does the moment of inertia of a solid and a hollow affect its speed? And this is kind of just the work behind it. And so that's the first question that we have. And the second question is having to do with this spring. Be short, and so I'm gonna go through it pretty quickly. Where there is a spring, and we know that the force of a spring, F equals negative kx. And we also know that F net equals ma. So in a system where there is no external or other forces, ma equals negative kx. And so what we need to find is we need to isolate k when given x equals a cosine t dx, or yeah, that's what we're given. And so what we've been doing, or what we've, I guess, did in the beginning of the year is how do we get, using distance, velocity, and acceleration? You derive it. And so the derivative of x is going to equal negative a, and you bring out the thing out. Sorry, this should be sine because it got derived. It's the derivative, no, if you derive cosine, it should be sine, but I forgot what that was called. I can't think of the phrase for some reason. And then now it should be negative. Since you bring it out one more time, you get that value right here. And so it's because if you derive cosine, it becomes a negative sign, and then sine, and if you derive sine, it should be cosine, but the sign doesn't change because the derivative of sine isn't negative cosine, it's cosine, so the negative just stays, whereas the derivative of cosine is negative sine, so that negative sign stays out, or comes out there. And so now that we have that, we have our x, we have our acceleration, and we just plug it in, where m times negative a angular or velocity times cosine equals negative a cosine. So we have this, and to find our k, I don't know if I might have forgot to mention that, but the entire point was to isolate k, the spring constant. It would equal m. I need to just bring that down, so cosine and so these cancel out, the negatives cancel out, the a's cancel out, and sorry, there should be no w here. And so everything on the bottom gets canceled out to where it's going to equal m angular velocity squared. It's a very simple, very just making use of the information that we learned in the first couple weeks of school, where we know that the distance formula, the derivative of the distance formula is velocity, and the derivative of that is the acceleration. So the double derivative of the distance formula is going to be the formula for acceleration. And so given that, since we set it up to where now we have acceleration and distance, we're able to plug in those two values, isolate the spring constant k, and find our value to be m equals the angular velocity squared. And so that's what I have for April 29th. I hope that you guys were able to take away stuff, the moment of inertia, the conservation of energy, now including rotational kinetic energy. And now here, just a reminder back on, okay, the derivative of velocity is acceleration, the double derivative of distance is acceleration, and plugging in the values, isolating basic algebra, stuff that we've been doing and should be doing as college students. And so thank you guys for watching, and I'll see you guys in the next one.